Okay, let's talk about this. We have all been there. You're in the lab, you're trying to get a super precise measurement, and this incredibly expensive piece of equipment, the precision balance, just refuses to play ball. It is a frustration every single scientist, technician, and student knows way too well. Well, today, we're going to finally make sense of it.
Right? You put your sample on the pan so carefully. You might even hold your breath. And the numbers on that little screen just keep changing. Is it the air conditioning? Is someone walking down the hall? Is this thing broken? That one problem is probably the source of more wasted time and bad data than we like to admit.
And, that's really the heart of the issue. For most of us, this machine is just a black box. We put stuff on it, and we expect a perfect number to magically appear. But here's the thing. If you don't understand what's actually happening inside that box, you're pretty much guaranteed to make mistakes. So let's change that.
So let's crack open that black box, shall we? How does this machine actually know that a tiny little pinch of powder weighs exactly, say, 1.05 grams? Well, the answer is pretty fascinating. And believe it or not, it has absolutely nothing to do with springs like you'd find in your bathroom scale.
The real secret here is something called Electromagnetic Force Restoration, or EMFR for short. The easiest way to think about it is like a super precise magnetic cushion. So when you place something on the pan, gravity pulls it down. The balance instantly senses this tiny movement and shoots an electrical current through an electromagnet inside. This creates a magnetic force that pushes the pan right back up to its starting position. And this really shows you the night and day difference in how these things work. See, a normal scale, it just reacts to weight. It measures how much a little piece of metal bends or stretches. But a precision balance, it's proactive. It doesn't really measure the movement, it measures the exact amount of electricity it needs to prevent the movement from happening in the first place. That right there is the key to its incredible sensitivity. And if you remember one thing from this whole explainer, please make it this. The balance isn't really measuring grams or milligrams, it's measuring milliamps. It's measuring the electrical current it needs to perfectly fight gravity and hold that pan completely still. The heavier the object is, the more electrical current it needs to push back. So that electrical signal then gets sent to a tiny little chip called an analog to digital converter, an ADC. This chip has one job: translate that flow of electricity into the number that you see on the screen. And it does this hundreds of times every second. And that is why any little vibration or a change in temperature or even a tiny draft of air can make the numbers drift. It's directly messing with that super sensitive electrical measurement. So now that we know it's all about measuring electricity, all those rules for setting up a balance suddenly make perfect sense, don't they? It's not just about being tidy. It's about controlling the physics of the entire room. Which brings us to the number one rule that, let's be honest, almost everyone breaks. You've seen it in the manual and you've probably just ignored it: the warm-up time. You have to leave the balance plugged in and turned on for at least 30 to 60 minutes before you use it. And trust me, this isn't just some random suggestion they threw in for fun. See? This waiting period lets all the internal electronics, the coils, the sensors, that ADC chip, reach what's called thermal equilibrium. It's simple, really. As electronics warm up, the way electricity flows through them changes. So if you try to waste something on a cold balance, the numbers will drift and wander as the parts inside heat up. Letting it warm up first just makes sure everything is stable and gives you a consistent baseline to measure from. And this is exactly why the location of your balance is so critical. Every single one of these things messes with that sensitive electrical measurement. A wobbly table? The balance sees that as tiny changes in weight. Direct sunlight? It heats up one side of the machine, throwing off that thermal equilibrium we just talked about. And an air conditioner draft, you might not feel it, but it's enough of a force to literally push down on the weighing pan and get measured. Okay, so our environment is stable. Now we've got to tackle the most common user error of them all: leveling the balance. It sounds simple, but if your balance isn't perfectly flat, your measurements will be perfectly wrong every time. Here's why. Gravity pulls straight down. Period. Towards the center of the Earth. If your balance is tilted even a little bit, the force from your sample gets split. Part of it pushes down like it should, but another part of it starts pushing sideways. This is called a cosine error, and it basically means the balance is only seeing a fraction of the object's true weight. Your reading is always going to be a little bit too low. So how do you fix it? It's actually really simple. Just look at that little spirit level bubble. Think of the bubble as always floating to the highest point. So if the bubble is at 12 o'clock, way in the back, it means the back is too high. Easy.
You just raise the front to match by turning both front feet clockwise. If the bubble is at 6 o'clock at the front is too high, so you lower it by turning both feet counterclockwise. And if it's off to the side, say at 3 o'clock on the right, you just twist the feet in opposite directions to tilt it back to center. It's a really simple fix for a huge source of error.
All right, our balance is warm, it's stable, and it's perfectly level. We're finally ready to actually weigh something. But now we face the final boss of the setup. Which button do we press? Zero or Tare? They look like they do the same thing, but they're telling the computer two very different things. You press zero only when the pan is totally empty. This tells the balance, okay, computer, this right here, this empty pan, this is my true absolute 0 point. Tare, on the other hand, is what you use after you've put your container, like a weighing boat, on the pan. Pressing Tare is basically telling the balance, hey, ignore the weight that's on here right now, just show me any new weight that I add from this moment on. So the correct way to do it is simple. 1. Place your empty container on the pan. 2. Wait for that little stability indicator. It's usually a small dot or circle to pop up. That means the balance has a steady reading. 3. Press Tare. The display will go back to 0. Now you can add your sample, and the number you see is the true net weight of just your material. And here's a cool little trick. After you've weighed your sample, if you take the container and the sample off the pan together, the display will show you a negative number. Guess what that number is? It's the exact weight of your empty container. It's just a handy way to double-check your work. Okay, to wrap things up, let's cover 2 pro-level topics that are going to keep your balance accurate for years and years: calibration and just basic care and cleaning. You might be thinking, if this thing is so smart, why do I ever have to calibrate it? Well, the answer is actually amazing. It's because the force of gravity isn't the same everywhere on the planet. It actually changes a tiny bit with altitude and even your latitude. So a balance that's perfectly calibrated in Denver, the mile-high city, won't be quite accurate if you move it to New Orleans, which is at sea level. Calibration just tells the balance, okay, right here, in this spot on Earth, this much electrical current equals exactly 100 grams. And look, to keep this very sensitive instrument working, please follow these golden rules. Always unplug it before you clean it. Never, ever, ever spray any kind of cleaning fluid directly onto the balance. It can get inside and completely destroy the electronics. Just use a soft, damp cloth. And finally, if you have a model with the glass doors, never, ever lift the machine by that glass shield. It is not a handle, and it will break. So, here's the real takeaway. It's not a black box. Understanding the science of how it actually works, from that electromagnetic force to why it needs to be warm, that is the absolute key. It's the difference between fighting with your equipment and getting perfect, repeatable data every single time. By looking inside this one black box, we've hopefully turned a common frustration into real mastery. So my question for you is, what's the next black box in your lab? What's that other tool you use every single day that you don't really understand? Because as we saw today, being curious about that is the first step to becoming a real expert.